Electron beam induced enhancement and suppression in copper nanoparticles in environmental scanning transmission microscopy. In this study, the oxidation of copper nanoparticles, which is of interest due to its wide application in catalysis, electronic devices, photonics, and nanomedicine, all of which are important in our modern life, is being observed in an electron scanning transmission electron microscope, or ESTEM for short. ESTEM is a powerful tool not only for atomic scale characterization, but also in situ catalytic experimentation, which can provide fundamental insights on catalysis and chemical reactions. While the electron beam in ESTEM can cause damage to the sample, it can also be used for fabricating nanomaterials or activating a chemical reaction by inducing atomic displacement, also known as knock-on damage, where an atom or set of atoms is displaced by another atom in a molecule, which causes interstitials and vacancies in the sample. This can lead to structural changes such as nanoparticle reorientation, recrystallization, enhancement of diffusional process, and mechanical deformations. The focused electrons can also reduce oxide nanotubes in specific regions, leading to the extraction and encapsulation of metal nanoparticles inside the nanotubes, changing its electrical properties. All this to say that ESTEM is a useful tool, and being able to have more insight on this tool can allow scientists to have more control of its use in creating materials and conducting studies in the future. In previous studies on the effect of electron beam irradiation on the oxidation of solid materials, some have reported an enhancement in the oxidation of metallic nanoparticles, while others have been shown to reduce or prevent oxidation, which is believed to be due to a result of cross-linking and the formation of a carbon layer. While it is known that the electron beam in ESTEM interacts with the sample, which may alter the sample and its properties, this study is being carried out to see if the ESTEM electron beam accelerates oxidation in copper nanoparticles and to what extent. Something known as the Nano-Kirkendale effect in metallic nanoparticles is caused by the higher diffusion rate of metal ions through the oxide shell than inward diffusion of oxygen ions, and it is hypothesized that the electron beam actively influences the reaction and overall accelerates the oxidation of the nanoparticles when compared to particles oxidized without exposure to the electron beam. It is also thought that the electron beam will enhance the Nano-Kirkendale effect through the creation of vacancies, which will consequently increase the diffusion of interstitials in atoms. In environments such as in this experiment, chemical reactions occur at the phase boundaries that lead to the generation of copper cations and O2 anions, which are transported through an existing oxide layer for further reaction between the reactants and additional oxide formation. These ions are being produced at both inner and outer interfaces of the oxide layer and diffuses through the oxide layer in opposite directions, so both an outward shell growing outward from the original surface and an inward shell growing inward can be identified. During this oxidation, Kirkendale void formation can be observed due to the faster diffusion rate of copper cations relative to oxygen. Some things need to be taken into consideration in this study, one being electron beam-induced changes in the local temperature, seeing that fast electrons interact strongly with both atomic nuclei and atomic electrons in a Coulombic manner. Most of the energy loss is attributed to electron excitation and can be calculated from the Bethe-Bloch expression, and as a major portion of this energy eventually ends up as heat, the local temperature rise can be estimated theoretically given a known specimen geometry. Another being sample charging due to the ejection of secondary core and auger electrons, electrons whose energy levels result from the relaxation of ionized atoms to a lower energy state. One thing that can be helpful to consider is that the electron beam potential can be in the order of the redox potential of the desired reaction, meaning that the electron beam potential can be adjusted according to the redox potential of the reaction to get the desired result. These aren't trivial to quantify and cannot be neglected in situ studies of electrodes, electrocatalysts, and catalytic redox reactions. Measures were taken to mitigate these variables in this study. The copper nanoparticles in the study were polycrystalline nanodiscs with an average diameter of about 85 nanometers. They were fabricated through a nanofabrication method known as whole mass colloidal lithography based on colloidal self-assembly lithographic patterning. Prior to the experiments, the samples were annealed in 3 millibars of hydrogen gas at 400 degrees Celsius for 1 hour in the ESTEM. This resulted in the copper nanodiscs transforming into hemispherical copper nanoparticles with fewer grains and were determined to be an average diameter of 70 plus or minus 7 nanometers based on measuring 20 of the nanoparticles. The oxidation of copper nanoparticles was studied at temperatures of 100, 125, 150, 175, and 200 degrees Celsius while being oxidized in 3 millibar of oxygen. All other microscope parameters were kept unchanged to minimize variables. In each of these studies, several particles were continuously imaged during their morphological evolution, recorded in real time using annular dark field ESTEM. At the end of each experiment, the oxygen flow to the ESTEM was stopped, and the remaining oxygen in the column was purged out and samples were cooled to room temperature. Once under high vacuum, the sample was moved to locate other particles on the same chip that had gone under the same oxidation conditions without having been exposed to the electron beam. The results from these experiments were compared to those of particles undergoing oxidation without exposure to the electron beam. The image on the slide shows an image of the particles at both the start and the end of the oxidation process while being exposed to an electron beam with the start and end time in each picture. In this slide, we can see the ESTEM particles that were not exposed to the electron beam during oxidation in Figure A and with exposure to the electron beam in Figure B. Comparing these images reveals that the electron beam had undoubtedly accelerated the reaction as the beam-on particles at all temperatures had reached equal oxidation values at an earlier time during the reaction relative to their corresponding beam-off particles. The extent of this acceleration, however, appears to have a temperature dependence, with larger differences observed between the times at which beam-off and beam-on particles reach equal oxidation fractions at lower temperatures, indicating the greater influence of the electrons on reaction rates at lower temperatures. Figure B on this slide shows the volume fraction of the metallic copper core lost during oxidation. In Figures C and D, we can see zoomed-in images showing the inner and outer layers of the particles with the dotted lines highlighting the boundaries between the two oxide layers. In Figure F, the ratio of the thickness of the inner and outer oxide shells for beam-on and beam-off particles at different temperatures is shown. What was observed from this was that the electron beam enhances oxidation as a result of the outward diffusion of metallic ions and suppresses oxidation due to the inward diffusion of oxygen atoms, demonstrating the important role that knock-on damage, charging, and ionization has in the ESTEM experiments. The ESTEM oxidation of copper was repeated at 200 degrees Celsius with half of the electron dose in order to observe if the electron dose itself had an effect on the oxidation enhancement. By comparing this result with the image of the nanoparticles oxidized at the same temperature with the full electron beam exposure, it is indicated that observed reaction kinetics have an electron dose dependence.